All right, recording restarted. All right, so number 54 is the first one that is circled. 54, let's take a look. Rank the torques of the 5 doors shown in this figure from least to greatest. Notice the magnitude of all the forces is the same. So here we got like a 10 Newton force. We're pushing with the same 10 Newtons, but in different locations, and one of these, a couple of these at different angles, different locations. I think the way I'm interpreting this is, I think the far left end is the door hinge. You see door hinge, door hinge, door hinge, door hinge, door hinge, right? So I guess the handle would be like the far right side. We'll go with that, right? And I got force vectors, force vector, force vector, force vector, force vector, force vector, okay? Causing torques. Now, number 54. Okay. You guys remember that torque is equal to R cross F. Okay. The last 2 days, you guys have been doing lots of these calculations. Okay. You could also call that the magnitude of R times the magnitude of F times the sine of the angle between them. I put my little vector arrows of these variables. These are all vectors, right? They're all vectors. Okay. Okay. You can only take a cross product of 2 different vectors to give you a third vector. Okay. All right. So let's check this out. These 5 doors with the same force at different locations and different orientations. Which one of those has the least amount of torque? A, B, C, D, or E? Here is a hint. Which one has 0 torque? E. E, right? Because you guys see the force is applied exactly parallel to the door, right? Let me show you guys exactly what that looks like. Sure, I have something about that. Right here, I'm at the door right now. What's going to happen if I push the door this way? Does that turn the door? That's never going to turn the door, right? So that's 0 torque, that's 0 turning moment. Yeah, that's E, right? So in terms of the equation, yeah, there's a radial distance. Yeah, there's a force, but that's 0 degrees because they're parallel to each other. Guess what is sine of 0 degrees? 0, right? So we got 0 Newton meters is equal to torque E, and that's going to be the least because it's equal to 0, right? So I'll say less than, and I'll have like a string of torques. Let's set up, right? So less than something, less than something, less than something, less than something. Okay. Right. Let's cap with the greatest torque. Right. Look at these 5 options again. Which one of those has the greatest amount of torque? A. A. Yeah. Because okay, so that force is at the full radial distance, and it's also at 90 degrees. So you're getting 100% of the value. So yeah, I think torque A is going to be the most. So I'll call it torque A is the most. So A is the most, E is the least, right? Okay. How about which one is the where do you guys think D ranks? Really high or really low?
Really low.
Really low, right? Because you're pushing really close to the hinges. So yeah, there's a tiny amount of torque, but hardly anything. You guys think that's probably gonna be like second least? Yeah. Let's go torque D right here. Okay. Right. So now we're down to B and C. What are we gonna do with B and C? Let's take a look. Okay, now B and C have the same force at the same location. Ooh, but which one is actually providing more torque? B, because that one's at 90 degrees, so you're getting like the full value. Sine at 90 degrees is like 100%, right? This one's, well, something less than that. Okay. Yeah, so I'm gonna go torque B is the second most, and then torque C, I know is, well, less than torque B, so it has to be like that, right? Right, you guys got that? So it goes E, D, C, B, A. Yeah, it's exactly reverse alphabetical. Right, you guys got that? All right, next one. Number 61, 2 gears. I think one of the very first projects we did, you guys remember, I think it was like the first week of school, you guys did a gear system. You guys remember that? We did like index paper and glue, and so it was kind of like this, right? We got one gear is larger than another. It's just large gear and small gear. Compare their angular velocities, like revolutions per minute, or we're going to do radians per second. Also compare the linear velocities of the teeth that are in contact. Right? Like maybe one gear is driven by a motor, and then that gear is connected, the teeth connected to the other teeth is driving the other gear, right? Right. Actually, I think I want to answer those questions backwards of how they asked them. I think it's easier to answer the second question first. Let's do that. So number 61. Okay. Let's say I'm comparing the linear speed of the teeth on the large gear to the linear speed of the teeth on the small gear, right? Large and small, right? So linear speed. Because if I point a radar gun at the teeth, that would tell me the linear speed, right? How about this? What if I point the radar gun right, bam, right there where the teeth are meshing together, right? Do you guys think as the teeth are flying through that same point, they have the same linear speed? Same linear speed? Yeah. In fact, the radar gun probably wouldn't be able to distinguish the difference, right? Whether it's the left tooth or the right tooth, or left gear, right gear, the same speed, right? So can I say equals? Right? Equals? All right. Right. Because that was question B. Right. Let's go answer question A, which is the angular speed. So angular speed of the large gear compared to the angular speed of the small gear. Right. Now, if you could see this in motion, or so I'm going to put some inequality here. Right. These will not be equal. Let's think why. Right. Because if you're watching these two gears spin, do you think they're spinning at different rates? Like how about this? How about this? Let's say you hand power the large one. You make one complete revolution. Right. Does the small one also make one revolution? Or does it make what, less than or more than? More than one. In fact, do you guys think you could compare the circumferences to get an idea of the ratio of how many spins they do? Right? Like, suppose you got 3 times the circumference for the large one compared to the small one. Right? If the large one makes one complete revolution, how many revolutions does the small one make? 3. Yeah, it would also be the same ratio. And you know what else I know about circumference compared to radius? Could I say that circumference equals 2 pi r? Circumference is directly proportional to the radius. So if the large gear was like 3 times the circumference, is it also 3 times the radius? You guys think? Right? Now, why am I tying this back to radius? Because I can use this poster to figure out something about the spin rates, the angular velocity. Right? Right? You guys remember this here? Right? We've already said that those two gears have the same linear speed for the teeth, same linear speed, right? So if you know, like a larger radius should have a smaller angular velocity, shouldn't it? Right? Let's do like this. Right? If v is the same for both, that's equal to omega large times r large, which is also equal to omega small r small. Right? Right. Omega and r each have like an inverse relationship with each other. Like if one goes up, the other goes down. Okay. So let's do a numerical example. Let's say the large one has a radius of like 30 centimeters, and the small one has a radius of like 10 centimeters. I'm just making up numbers just for example, right? But that's a good thing to do, right? If you ever have like an abstract problem or something just in terms of general variables, right? I mean, if you can get it, you can get it. That's awesome, right? But if you need to pop up some numbers and kind of play around with it, then yeah, go ahead and do that too, right? I'm gonna say let's do like about 1 radian per second. Right, I'll say equals v equals. So I'm just gonna skip straight across the v and just say this product equals this product. Right. So we're getting a numerical example now. Numerical answer. How fast is my small gear spinning? Three radians per second, right? Because 1 times 30 equals 3 times 10. You guys see that? See that? Right. Okay, so I bet maybe everybody here has this answer by now. Which way does the inequality go? Does it go this way? Yeah, there you go, right? That's because 3 is greater than 1. Yeah, right. Right. Number 62. Ooh, videotape. Right. when a videotape is rewound, why does it wind up fastest toward the end? Ooh, right. I think we're talking about like a VHS. Have you guys ever played a VHS? Oh no, okay. Have you guys ever played a cassette? A cassette? Yeah, okay. It's the exact same idea. They could have said cassette. It'd be the exact same principle here. Here. I'm gonna draw a picture for you guys. Oh yeah. Old man Griffin breaking out his 20th century knowledge right here. Oh yeah. Yes. All right, so I'm drawing a VHS tape, but you could think of this being like a cassette, and it's the same idea, right? It has a couple of gears in here. Now, one of these gears is driven by a motor, and the other one just like naturally tags along, right? It's got like a roll of film, right? So let's do a roll clip. Let's say this whole thing is completely played through, so it's like at the end, right? So look, we do something like this, and we've got the whole roll of film around this one. Right, roll. So we just played the whole movie, and like here's the end credits, and it's rolling by. It's like copyright 1981. Okay, so we got all that. Right? And then we need to rewind this thing. So we're gonna hit rewind. Gonna wait a few minutes. Go right, and this gear right here is connected to a motor. So the motor is and it's rotating, and we're watching this thing rewind. Okay? So sometime later, it's gonna look like here. I'll draw what it looks like sometime later. Might look like this. All right, and we're still waiting, right? And then we come back like a minute later, right? And it's still rewinding. So I'm doing like a time lapse, right? Right. And then later on, it looks like this. Until finally comes to a stop, right? And now it's at the first frame, right? And then we hit play, and then we see like Indiana Jones come out with this mysterious hat, like who's that guy? Right, so here's the beginning, right? Now it's ready to go. All right. Now this process, if this motor was connected to this left gear, probably the easiest way to engineer this thing is to engineer it so that it has a constant angular velocity, right? So let's have that premise. How about if omega is constant, right? Wouldn't that be the easiest way to have it do like if I did like 1 revolution per second, for example, right? It turns around once, right? Turns around once, right? Look what's happening to like the circumference of this. Here's a little tiny radius. Here's like a medium radius. Here's a huge radius, right? You guys see the radius getting bigger? Right? So if it's rotating constant, I haven't finished the thought here. This is the beginning of a sentence, right? Right. Then what would happen to V? Well, the answer is right on this poster right here. V is omega r. So if omega is constant, but the radial size is getting bigger, do you guys see V also gets bigger? Like the linear speed of that tape, right? Let me go ahead and write that down right here. V equals omega r. I'm gonna use this as a framework. Okay? So if omega is constant, then V, the linear speed of the tape, is directly proportional to the radius of the tape. So as radius increases, V also increases. Right? Maybe that's the way I would write that. I think that should be sufficient. Right. That makes sense. All right. All right, you guys ready for our next one? Next one I want to do actually is one I didn't circle, but I want to talk about it anyway. That's number 68. You guys see number 68, tightrope walker? Let's think about this guy a little bit. Right. It says tightrope walkers often carry long poles. And why would the long pole help maintain stability? Now, I think they're looking for like multiple answers, but I for sure know at least one. Yeah, what do you think?
We answered this question.
No, I just want to talk about it. Right. Hey, you guys ever done that? You guys ever tried to like maybe you're like walking along a pipe or something that's kind of difficult to balance? You guys ever hold your arms out? Yeah, that's the same effect, isn't it? Right. But like physically, what are you changing? Are you changing your center mass? No, you're not changing your center mass. You're not changing your weight. What are you changing?
What?
Yeah, what are you changing? Not your center of gravity. Winner, moment of inertia. Yeah. aka rotational inertia. Exactly, right? Here's your long pull, right? Now, I guess it's not spinning horizontal, but maybe like vertical, it turns kind of vertical. Same idea, right? 1/12 ml squared. Maybe here could be the mass of his pull and the length of his pull, 1/12 ml squared. He's given himself a bunch of rotational inertia, right? When you hold your hands out, it's the same thing. You're distributing your mass like further from your center of gravity. Kind of like the figure skater. Same thing, right? Hold our arms out, large I value, right? And so when this guy starts to topple over, let's say he has like some error in his walking, he starts to topple over the rope. Easy to do, right? Then it's really hard for him to change his orientation. It's actually really hard to topple over because he has so much inertia in a rotational sense. It's really easy for him to correct himself. So he stays back on the rope. Okay. All right, number 74. Last class, this is the last one I did. So this will be the last one we do today. Number 74. A steering wheel is rotated. Oh, we got a picture right here. 128 degrees, right? As shown in this figure. The radius is 22 centimeters. How far would a point on the end move? Right? Now that sure does sound a lot like this right here. Right? Did you guys remember the first time I showed you this poster was a few weeks ago? I said you probably learned a specific version of this formula back in elementary school. Did it go like circumference equals 2 pi r? Do you guys remember that? Circumference equals 2 pi r, right? So you probably learned that years ago. Now you're seeing the more general version. What if you don't make exactly one revolution? What if you make like any turn, right? And here they're going 128 degrees, right? Now that 2 pi is actually an angle in radians. It represents 360 degrees or one revolution, but it's in radians. That's what 2 pi is, right? Now we're not going to have 2 pi. We have 128 degrees. Before we actually do any math, to solve this question, isn't it true we have to convert this to radians? Convert to radians? Okay, so we have to convert to radians first, and then we can apply that expression to get how far a point on the edge would move, say like in centimeters. Right. So theta equals, now this is at 128 degrees. Right. Let's convert that to radians. So how do you convert degrees to radians? How many like what's the conversion factor? How about this?
Idea.
Guys, one trip around the circle, that's called one revolution. How many degrees is that? 360? How many radians is that? 2 pi? Right? Can I say 2 pi radians is equivalent to 360 degrees? Right? Alternatively, let's see how I did it last class. Where's my notes from last class? Did I lose? Oh, okay. Here's how I did it last class. I did pi over 180. Guys, is that the same ratio? 2 pi 360, pi 180 is that same ratio? I got 2.234 radians. Okay, which is a lot of digits, but I'm going to save my rounding for the end. Okay, great. Guys have that? Okay. Next thing, let's do how far it moves in centimeters is equal to theta times r, right? Remember, this is a more general version of circumference equals 2 pi r, right? But now we don't necessarily want one revolution exactly. So I'm going to go 2.234 radians. Oh. And the radius is 22 centimeters. Or if you like, you call it 22 like centimeters per radius. Cancel out the radians. Okay. Let's do 2.234 times 22. 49.1 centimeters. Bam! Just like that. All right, that worked out for you guys. All right, you guys good so far? All right, we are about at the end of class, so that's going to be our pause point. Yeah, remember, check out the sky tonight. We might possibly be able to see Northern Lights. I don't know. We're going to find out, but it'd be cool if we do. And the computer storm will crash. Also be cool.